All right. Good evening, Tanisha and Pranav. Thanks for joining. So I
Good
hope.
evening, sir.
Thank you. So I think more people will join soon. So let them join. We will start today's class. So uh, what do I have here is today I have one question regarding electrical rockets. So um yeah, I think this question itself will take us a lot of time, so that's why I selected only one question. Before we start this question, do you guys have any quick questions you want to ask?
No, not from my side.
Okay. All right. Um, I guess Tanisha also doesn't have any questions. So so today's question is going to deal with something called resistor jet, right? So something professor must have taught you in electrical rockets. Uh, the reason I selected this is in your homework problems. I think there is this arc checked thruster, and this is more or less similar to that. I mean, you can apply the same concepts over there. So that's why I selected this question, so that it will not be exactly same as homework problems, so that you will get a uh, chance to think and then apply. And also, since this is not been taught, or this is not been taken to a depth in the lecture, so I thought this solving this would be a good exercise. So the what the question has is that an ammonium gas resistor jet is used as a thruster. So resistor jet is something that because of electrical resistance we are trying to heat the uh, gas, and here we have ammonium gas. uh, and these thrusters are actually used in attitude and orbital control and station keeping of geosynchronous satellites. Okay, so attitude is nothing but the orientation. That's what we call it, attitude. Orbit control, like orbit parameters, which whether we need to change the orbital angle, and also station keeping of geosynchronous satellites. For that, we use small thrusters fitted in along the around the body of the satellite. Okay, so and the thruster is going to be resistor jet, and it is going to generate a thrust of 10 newtons with a specific impulse of this much. Okay, that is also given. The expansion ratio of the nozzle is 80, so resistor jet also it heats the gas and then is going to expand in the nozzle, so that's why we have an expansion ratio of 80. And specific heat ratio of ammonium is also given, and ammonium gas is initially stored at 300 kelvin. So the cold gas is actually at 300 kelvin, and because of resistance we are going to heat up. The ambient pressure of a geosynchronous at this much altitude would be 0, which we all know is going to be uh, vacuum. And if the pressure at which ammonia is heated is 0.5 megapascal, which is nothing but the chamber pressure is 0.5 megapascal, what we are asked to find is determine the electric power required to for resistor jet. I mean, amount of electric power we need to supply uh, for heating the ammonia gas. Okay, and we need to assume an efficiency of 75% for that. And while heating, temperature is going to reach a very high temperatures like 1000, 1500, 2000 kelvins, and dissociation of ammonia can happen, right, because it's a gas. So for the first question we are going to neglect the dissociation. If we neglect the dissociation, what is the amount of power required is what we are going to find out. And for the second question, let's say if we assume a 10% of heated ammonium gas is dissociating. So if the ammonium dissociates into nitrogen and hydrogen, let's say if 10% of the ammonia gas is dissociating, what is the amount of energy lost, right? So what is the because of dissociation there will be some energy lost, so what is that amount? And third is, because of that dissociation, what is the how much specific impulse am I losing, or what is the change in specific impulse I am going to have because of dissociation, is what we are going to find out. These are the three questions. It might look trivial, but it is not. trust me. So I hope the question is clear for you all. So let's say if I try to draw a schematic so that it would be easy to understand. So resistor jet would look something like this. Okay, so there's going to be some combustion chamber, and gases are going to come, right? And then you have heater which is going uh, circumferentially. So that's why I just drawing a cut section here. And then gases comes, gets heated up, and then it is connected to the nozzle, okay, where it gets expanded. It's a simple schematic. So now the temperature with which it enters is 300 Kelvin. Since 300 Kelvin is less, let's use blue color. T naught is 300 Kelvin, and the thrust you are going to get, the thrust is going to be 10 newtons, and ISP is also given. Okay,
Yeah, ma'am, you got it.
let me, so let's say if I want to write the given temperature is 300 Kelvin initial temperature, the thrust is going to be 10 newtons, ISP is also given 2200 newton second per kg. Okay, and what else is given? I think expansion ratio is given of the nozzle, which is 80, and specific heat ratio is 1.31, and then pressure, chamber pressure is zero point 0.5 megapascal. All right, I guess that's it. And the ambient pressure, P ambient is equal to nothing but 0 pascal because of vacuum conditions. Okay, now we need to find the power required, and for heating, for electrical heating, we have 75% efficiency. Okay, so this is the problem statement. So ammonia gas is going to come, it's going to get heated up by the uh, electrical resistance heating, and it is going to get accelerated in the nozzle with the expansion ratio of 80, and we should get 10 newtons of thrust and ISP this much. Okay, I hope the question is clear to everyone. uh, we need to find the power from this. So we need to find power, power required for heating. So while heating you are giving some power, electrical power. What is this power is what been asked. This is a question A. So what do you guys think? How do we proceed this problem? Any idea? Anyone want to take a guess?
So, so here we are actually heating the ammonia
Right, right.
from 300 Kelvin to some final temperature.
Hmm. Correct.
So so that it gets pressurized at zero point 0.5 megapascal.
Right.
So it goes from T1 to TC.
Hmm. 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 Right.
That means with 0.75 efficiency,
Hmm.
the heat so that can be done.
Okay, so the
So
amount
as
of heat required to, so amount of energy required to heat
yeah,
ammonia gas from
from
T naught
T1
to
to
Tc.
Tc.
That is absolutely right.
Yes,
So
yeah.
let's say if I want to write it in a mathematical form, you can say Q required, Q heating is nothing but efficiency times the power required, right? So we need a higher power. So or you can write divided by efficiency on the other side. Okay. So this is the power we need to find out. But Q heating you can write it as Cp times delta T, where delta T is going to be some T of chamber temperature minus T naught. Uh, but since we are talking in terms of power, we need to multiply by m dot. Okay, m dot Cp delta T is equal to eta P. So this is what we need to do. So, but what we know is we know the eta C, eta. We know Cp of Cp is going to be ammonia gas. So Cp of NH3 is given, no problem. In the question, it's given as 35.06. So Cp of NH3 is given joules per mole Kelvin. This is going to be molar basis. So T naught is also given, but the question is we need to find out m dot and Tc, right? These are the two things we need to find out. How do we find out m dot and Tc is the question.
M dot can be found from the ISP and
True.
thrust.
Okay, it's going to
In
be F by
F by
ISP.
ISP.
Wonderful.
Uh,
So this is going to be
I got 4.545 gram per second.
4.545
Is it?
gram per second. Okay, let's
Gram per second.
10 power minus 3
To 10
kg
power
per
minus 3 minus
kg per
kg
second.
per second.
Okay, wonderful. Now the TC is going to be, how do we find TC?
Sir, Tc by T naught equal to P ambient upon Tc to the power gamma minus 1 upon gamma
Okay,
by
interesting.
using this formula.
TC
Yeah,
by T
adiabatic.
T naught is equal to P ambient by PC power gamma, right?
Gamma minus 1 by gamma.
Okay. Why did we select this? But T ambient we don't know, right? If you look at it, this T naught is the ammonia gas temperature with which ammonia gas enters. Space is not at, let's say, 300 Kelvin, right? So I have something like a tank where I'm storing ammonia gases 300 Kelvin, and that is what I'm supplying. But the whole thing is at the outer space. It's in the geosynchronous orbit. So you are actually doing isentropic relation from Tc to T naught, like Tc to T ambient, right? So that is how you are getting there, but we don't know the T ambient, or we don't
Uh,
know the T
but
exit.
but but by this formula, I think P ambient is 0, right? So
P
it
ambient is
won't be
again,
applicable.
yeah, P ambient is also 0. Actually we cannot use P ambient since it's an so the whatever the this thing you are referring to is actually isentropic expansion of gas, right? Isentropic expansion of gas. So actually what we will do is we need to apply it for Tc to Te exit temperature, and also Pc to Te P exit pressure, exit pressure will, there will be some always some pressure, it will not be equal to 0 Pascal, because gases are expanding, there will be some pressure at the exit. So this is where you can apply this equation. So is that clear why it is not possible to use this equation? one thing is T naught is at the different place, and P ambient is not equal to P exit. Those are the two reasons. So if you cannot use this formula, how do we find Tc? So in your assignment problems, usually I think power is given, so you will just directly substitute the power and you find the Tc from this equation itself. Probably that's what I think. Only if you do, we will come to know. But here we are asked to find the power also. So we need to use some other quantity to find out the temperature. So there are a few other quantities given, right? So we have been given the expansion ratio, we have been given gamma, so PC is also given. So we may need to use all these things to find out TC.
From uh, from the formula of the area ratio,
Mm-hmm.
we can find the exit pressure,
Okay.
and from that we can deduce the exit temperature
Okay.
from isentropic adiabatic equation.
But the question still remains: what is the TC, right?
Sir, either we can find the value of Mach number, then
Okay.
we can use the formula of Tc by T equal to 1 plus gamma minus 1 by 2 into Mach number square.
Yeah, that we can do. But to find Mach number, we need to. What do we need? Uh, Wait. So let's say. Okay. So let's go step by step. Let's. So you guys are almost right. So we have expansion ratio of 80. Let's try to find out the exit pressure first. Then we will come to we'll get an idea. So what would be the equation? So we have a very big relation here. Let me try to write it down here. So 2 plus gamma whole power 1 divided by gamma minus 1 PC by PE whole power 1 by gamma whole divided by gamma plus 1 by gamma minus 1 into 1 minus PE by PC whole power gamma minus 1 by gamma, okay, whole square root. So this is the relation for the expansion ratio, right? So from here what we can get the PC or PC by PE or PE by PC. Would be able to find it out. Gamma is 1.
Actually, it's very difficult to find
Right. So
because
that.
the equations you will get. Uh, uh, we can find it on the scientific calculators actually,
I see. Okay.
but it's not very feasible to find it out directly from hand
Hmm.
calculations.
True. So actually, it's a nonlinear equation. You may need to use scientific calculator to find out. Let's try to simplify. I have a easier way to do it. Um, what would this happen? So let's say summation epsilon equal to 80 is equal to. So let's how much is this part coming out to be? So 2 by 2.13 plus 1 would be something like 0.8658 or 1 divided by 0.31, okay, and multiplied by PC by PE whole power 1 by gamma. Gamma is nothing but 1.31 divided by gamma plus 1 by gamma minus 1 is 2.31 divided by 0.31 is around 7.45 16 into 1 minus PE by PC whole power 0.2366, okay, the whole square root. So if you just simply substitute, this is what you will get. And the problem is you have a non-linearity here. So you have this in the this is, so let's say if you consider PC by PE is the unknown, or PE by PC is the unknown, it is coming in both numerator and denominator. It's a non-linear equation. You cannot directly find it by simplifying this relation. So what you can do is you can use scientific calculator. For that you need a further simplification, or you can just simply use you know the tools, software tools like MATLAB or something. Okay, so if you guys want, I can quickly show. You can just use MATLAB's fsolve function to find PE by PC. Okay, so let me just quickly show. So let's say you take PE by PC as your you know what do you call, unknown. Okay, PE by PC is unknown. First you find PE by PC, and then you can find PE, or PE by PC itself would be enough for you to solve this problem. Okay, so are you guys familiar with MATLAB?
Yeah, just a little bit, not
Okay,
much.
no problem. You so give me a minute. So what do I have here is, let me show you here. So we have something called fsolve function here. Okay, so the fsolve function would look, give me a minute.
I use a scientific calculator. I
Huh.
got the ratio. Oh wait, no. There's a mistake.
Okay, no
I,
problem. So I hope you guys can see the window. You just, this fsolve is to solve a system of linear non-linear equations. Okay, so what we are going to do is we are just going to code this equation. Let's say for example equation is the variable, and you have to give x as a variable which you are going to solve. So at x will take it as a, will assume the whatever you write after this to be an equation. Okay, so let's say if you do 0.8658, okay, we just need to code this equation 0.31 times this is PC by PE, so it will be 1 divided by x power 1 divided by 1.31, okay, and then divided by square root of 7.4516 times 1 minus x power 0.2366. And since it's an equation you are writing, you need to take the right left hand side also to the right, so minus 80. If you put that, so this is how your equation looks. Okay, so at x, this is the equation which you are planning to solve for. So now you just write fsolve, this is just equation solving, and then you need to give a starting point to initiate the iteration. So this is, you have to do it in a using numerical methods. So it will be, you need to start with certain initial conditions. So let's say if I give 0.1 as an initial condition, and then if you do, well, so then it will give you a value which is 5.2895. okay, so this is 5.2895 into 10 power minus 4. So this is the x value basically. Okay,
sir, I am getting 5 point something 164 something.
into 10 power minus 4.
Yeah, yes, yes, yes.
Ha, that's
I,
great.
I think you considered the calculated values.
Ha
I
ha ha.
directly use the absolute values in the equation.
Directly, okay. Ha ha ha. Then yeah, that also you can do. So this is one way to solve the problem. Just I thought I will show you. This is a quite helpful thing. Here it's a equation is simple, but if you go into a little complicated relation, then you may need to. So then you may need to. Uh, you can rely on this MATLAB tools. Okay.
Sir, is it possible that such questions will come in the exam?
No, no, no. So I just thought I wanted to introduce a little advanced tool. That's why I actually thought I will show you. But it can be solved in scientific calculator. Again, even that won't be coming for your exams because you will not be having a scientific calculator. You'll be having a on-screen calculator. So you no need to worry about that. But I think this you can explore. So, what Pranav you got? Let me write that down also. 5.17 is it?
5.1637 into
1637
10 power minus 4.
10 power minus 4. So, this is from MATLAB. This is what Pranav got. Alright. So, we can use either of them. Okay. Now, we got PE by PC. PE by PC. We can find the pressure at the exit, but it is actually not needed. Uh, okay, so now we know the PE by PC. How can we find the TC? Is it possible? So again, if you want to use the isentropic relation, you need to know, you will be able to find TC by TE only, where both are unknowns, right? You will be able to find TC by TE, but you need at least one to find the other. Any idea? We can still use a lot of parameters here. So uh, chamber pressure is known. We need to find the chamber temperature. We know expansion ratio to be 80. uh, what would lead to 10 newtons, right? Or 10 newtons or ISP, what would lead to this, the chamber temperature, right? So can we use this ISP to get chamber temperature?
Yes, yes, yes. We have the
Right,
formula.
right.
Under root.
So okay, so let's say if you write ISP is nothing but C star times CF, right? So C star is a function of temperature, TC. So we can use this. CF is a function of epsilon, which is, we know, we can use that also. CF is actually function of epsilon, PE by PC and PA by PC. Using all this we can find CF, and then you can find C star, which is going to be a function of temperature, the temperature and molecular weight, which we already know. Molecular weight of ammonium is something like 17, right? So since using this relation, we will be able to find the temperature. So what is, do you guys have a ready-made equation for ISP as a function of temperature?
The under root 2 gamma y gamma minus.
But okay, so that is the jet velocity, right?
Yeah, yeah, jet velocity.
But that is assuming you have a perfect expansion. So jet velocity is this, but jet velocity will be equal to ISP only if it is a perfect expansion, right?
Yeah.
This is partly right, but there will be additional term. So what will you have is, ideally ISP is nothing but force is nothing but m dot into, or the thrust is nothing but m dot into Vj, plus there will be a pressure term, right? What is that pressure term?
PC minus PA into area of throttle.
I think it's PE minus PA. This is at the exit, right? PE minus
Higher
PE
PC minus
minus
PA.
A into area at the
Yeah.
exit, right? So now ISP is nothing but F by m dot, so which makes it Vj plus PE minus PA times AE by m dot. Now if you substitute, m dot is nothing but what is m dot, or C star is nothing but PCAT by m dot. If you substitute this over here, what you will have is ISP is equal to Vj plus PE minus PA divided by PCAT by C star. So PCAT into AE into C star. So this is what you will have. So please note this additional correction term, so you should not miss this. Okay, sorry about that. So now if we try to simplify this further, it's going to be PE by PC minus PA by PC into AE by AT, which is nothing but an expansion ratio, times C star. Okay, so we know PA is nothing, PA is 0 pascals, so we can ignore that part. So this will become Vj plus PE by PC AE by AT into C star. Okay, this is going to be ISP at vacuum conditions. Okay, so this is what we need to use to find the so Vj, as Pranav said, we can use this formula, and this will have Tc, and then C star formula will also have Tc. Let's substitute that also. So let's substitute everything together so that it will be clear for everyone. ISP at vacuum conditions is equal to 2 gamma by gamma minus 1 RTC 1 minus PE by PC power gamma minus 1 by gamma square root. This will be Vj plus AE by AT is epsilon, and then PE by PC we already know. Now C star is nothing but 1 by capital gamma square root of RTC. Now we just need to find Tc from here, that's it. So because we know everything else. Okay, is that clear?
Yes.
Okay, all right, so let's try to substitute the formulas. Maybe we can take RTC together on the other side. So ISP vacuum condition, this is at vacuum conditions only, so 2200 is equal to square root of RTC into you can write epsilon PE by PC into 1 divided by gamma plus 2 gamma by gamma minus 1 into 1 minus PE by PC power gamma minus 1 by gamma into square root. Okay, that's it. So let's write the capital gamma relation also. It's going to be square root of gamma into 2 by gamma plus 1 whole power gamma plus 1 by 2 times gamma minus 1. Okay, so this will be something where gamma is 1.31, which is given in the question, and we have PE by PC is nothing but 5.11637 into 10 power minus 4. Okay, this is 1, and then epsilon is 80. So if you substitute all this, what will happen? R is nothing but 8314.5 divided by 70 joules per kg Kelvin. Okay, so if you substitute all this, you will get TC. Can you guys tell me what is the TC is? First, maybe what is gamma? So 1.31 plus 1 divided by 2 times 131 into 2 divided by 2.31 so 2 square root of so capital gamma I am getting something like 0.6691. I'm not sure, please cross check once. And then if you substitute all this, how much is the temperature coming out? Let's see. 5.1637 10 power minus 4 power 0.31 by 1.31 1 minus answer into 2 1.31 divided by 0.31. So this part is coming out to be 2.653 and this is 80 into 5.1637 into 10 power minus 4 divided by 0.6691. This is 0.0617 is 2.653 2200 square divided by 8314.5 into 70. So how much are you guys getting? So the calculation I got is around 1342.7, like 43 Kelvin. How much did you guys got?
Just a moment.
Sure,
Calculator.
sure. After we find the temperature, that is the main thing, then we can directly substitute it here. Dot Cp Tc minus T naught to eta P. Is it coming around 1340 kelvins?
I'm getting around 1122 something.
1122. So how much is
Yeah.
this part coming out to be? So something around
Mm,
2.6 it was coming out to me for me.
it's just
So
a minute.
because the other part is actually minimal, it's very less, around point zero 0.06. Anyone else were able to get calculate this? 37. So 5.1637 into 10 power minus 4 power 0.31 by 1.31, 1 minus answer.
I got 2.653.
653. This part, the first part would be 0.06, something like that, right? 80 into 5.1637 into 10 power minus 4.
My answer varies, I think, because I directly substituted the values. I didn't individually calculate anything.
Even if you do
So
that,
maybe
but how much did you get? How much did you get?
it, it was something 1123 or 1122 something. Because
1123.
yeah, because the temperature is under root, so I have to take the whole term squared. Then I have to divide it by some r of that NH3.
Right. Even if you do that, this much change is too much, I feel. So you are telling you made this to be square. So you are telling
Yeah,
this
means
you made it to
I took
square.
the whole
This also you made it square,
yeah
right?
I took this whole bracket below the ISP 2200 and that whole thing squared then divide by 1 by r
Okay, let's say if you
into
do.
1 by r, sorry.
Ha. So even if you do that, still you will be having the
Uh,
same thing, right? So 2.653
just
plus
that
0.06,
into
0.06
plus
whole square,
minus
2100 whole square.
minus 1.
So again, I feel like you will still get the same thing into 17.
Uh, oh, I got the mistake.
Okay,
Got
okay,
the mistake. Yeah, 1342. 1342.
okay, wonderful.
Sorry.
So the temperature is around 1343 Kelvin or 1342 Kelvin, and now you can directly find the power required. So this is the amount of heat you need. You need to amount of power required to heat from 300 Kelvin to 1343 Kelvin. So let's say if we substitute m dot, where is m dot? M dot is 4.545 into 10 power minus 3. 4.545 into 10 power minus 3. Cp is 35.06, but it is in moles. Here it should be in kgs. Sorry, it should be in per mass basis, so it should be divided by 17 into 10 power 3 or 17 by 10 power minus 3, uh, and then we do not have space here. So and then you multiply it with 1343 minus 300 Kelvin divided by 0.75. Okay, so how much is the power coming out to be?
Uh, one 13035.26.
13035. Okay,
Point two six.
13.035 kilowatts.
Yeah, kilo.
So this is the total power you supply to the electrical heating you have here. So let me go back to the question. So this is the total power you supply to the electrical heating, and you see that the, what did they say, the efficiency is, assuming efficiency of electrical heating of ammonia, so it is only for heating. Okay, so that is, the efficiency is 75%. So upon including that, total is 13.0 kilowatt is the power you supply to heat the ammonia gas from 300 to Tc. Okay, now the temperature here is around 1300 Kelvin. At this point, ammonia can dissociate or may not dissociate. uh, so currently we neglected dissociation to find the, and we found the electrical power. Now let's say the second question is, so I hope the first question is clear for everyone. It's a lot of algebra, but
Okay, Jesus.
okay. So uh, we found the electric power. Now we need to see, let's say if first, in reality what happens is at 1300 Kelvin we don't know how much amount of ammonia is going to dissociate to nitrogen and hydrogen, but to find out we need to take into account of second law of thermodynamics, we need to take into account of equilibrium uh, constants and all these things, which we are not dealing in this course. So that's why in this question I have explicitly stated that 10% of ammonia gas which is heated is dissociating into nitrogen and hydrogen. Okay, what is the amount of energy loss due to dissociation? Because of this dissociation there is some energy loss, because NH3 has dissociated into N2 and H2, there is going to be energy loss. What is that amount? Okay, that is what we are going to ask. And we are trying, the standard heat of formation of ammonia is 46 kilojoules per mole, that is given. So now how do we find the amount of energy loss due to dissociation? Any idea?
The dissociated. So actually, the dissociation happens by absorbing energy.
Correct.
So we can find out how much was dissociated. We
Ah,
have mass flow, right?
true. So
So
for
you
that,
can find how much was dissociated.
right. So for that we need to write an reaction. Okay. So we have 1 mole of NH3, let's say, that is going to dissociate and give 10% of NH3 is only dissociating. So remaining, uh, so it is going to dissociate and it is going to have NH3, H2 and N2. So what are these amounts is going to be? So we know 10% dissociation, which means 90% of 90% of ammonia is going to stay like that, right? So if that is the case, you have 1 mole of nitrogen, ammonia here. So which is going, which after dissociation what is going to happen is you will have 0.9 moles of ammonia. That is the 10%. 90% of ammonia will just stay. Remaining 10% is going to dissociate. So then what is the moles of H2 and N2 you will have? You can just simply balance the equation, or we know 1 mole of NH3 if you want to dissociate, it is going to produce half a mole of N2 and 3 by 2 mole of H2. Here it's zero point 0.1 moles of NH3 is going to dissociate, so which you can maybe write it like 0.1 times 3 by 2 and
Yeah,
0.1 times,
0.3 by 2 H2 and 0.05 into.
exactly. So either you can write it like this, as you said, you can write 0.3 by 2 and 0.1 by 2 or 0.05. Okay, so you can do balance of hydrogen and nitrogen to get those two relation, and this 10% you use it to get zero point 0.9. Okay, now that you have found this, um, how do we find the energy loss due to dissociation?
We were previously given the, I think, some other values to
Right, so we are being
use them.
given NH3 to be equal to minus 46 kilojoules per mole. Okay, this is the additional value is being given. So using this, how do we find?
Can we say point one of 46 kilojoules is what is lost due to dissociation, or 4.6 kilojoules per mole?
Yeah, that is that is right. So actually, how do we actually we should do is the you should do a enthalpy of formation balances between these two. Okay, so between the right hand side and the left hand side, when we do that intuitively, as you said, we will have only zero point 0.1 times 46 kilojoules is the amount of energy lost. So let's do it in a systematic way. Let's say we have enthalpy at the reactant side. Okay, the formation enthalpy, how much would that be? 1 times delta HF of NH3. And similarly, the formation enthalpy of product side is going to be zero point 0.9 times delta HF of NH3 plus 0.3 by 2 times delta HF of H2 plus 0.1 by 2 times delta HF of N2. And the formation enthalpies of hydrogen and nitrogen we already know, it's a naturally occurring gas at naturally occurring state. So these two will have zero formation enthalpies, which we already know. And the difference between these two, which is going to be delta H of dissociation, or the energy loss due to dissociation, is going to be HF of reactants minus HF of products. So ideally you will end up getting 0.1 times delta HF of NH3, because that is the amount of ammonia we are dissociating, so that much amount of formation enthalpy is lost. So as Ram sir rightly said, it's going to be minus 46 kilojoules. So 0.1 is the mole, so it becomes only kilojoules. Okay, it should be minus 4.6 kilojoules. This is the delta H dissociation. So sometimes what happens is, during dissociation you may not form hydrogen and nitrogen as a gas, you may end up forming hydrogen atoms. So I think that is one of your questions in the uh, in your assignment problems. So you should be little careful. So those formation enthalpies you need to take into account. So that is why I brought this up. Okay, is that clear? How did we arrive at this? While we intuitively say it's going to be
Yes,
zero point
yes.
0.1, we have to be we have to take this and do proper balances to get it. Okay, all right, so I guess this is done then. So we know how much of energy lost. Now the next question is, because of this dissociation I am going to have a performance issue. I'm going to have a lesser performance at the exit of the nozzle. So what would be the change in specific impulse because of this difference in because of the dissociation, and how do we calculate that? Any idea how do we calculate it? So because of dissociation, what is happening? If we understand that, we will know what is the reason to decrease in efficiency, what is the reason for performance loss because of dissociation.
First of all, the heat is lost,
Right.
and and only zero point 0.9, I think, so 90% of NH3 is being used for genetic thrust.
Well, it's 90% NH3 is
So
there,
they tend to,
but you also have hydrogen and nitrogen instead of other 10% of
yeah,
gas.
they are also there.
They are also there. So your mixture of
They
gas
but
is going to be like
because
this. Yes.
so I think the 90% NH3 the and the other H2 and N2 is used for to generate thrust.
Mm-hmm. Right.
So, so that I think that 10% NH3 causes the loss of thrust.
Right. Uh, but how do we add the contribution of N2 and H2? So I'm trying to understand your answer in terms of some physical concepts, right? So there is going to be some change in ISP. My question is, uh, during dissociation, what is that happening, which is affecting the change in ISP? One thing you stated is NH3 has reduced. NH3 content has reduced. Now it is just now it's a now it's a zero point 0.9 NH3 plus
So the
QH2.
temperature.
So temperature is also one thing getting affected. So this is a composition. So composition has changed. This is going to affect your performance. Okay. Number two is the temperature will get affected because you have dissociated. You have lost some heat, and how do we get that heat? When the ammonia has heated to a very high temperature, it has some certain enthalpy, and if some ammonia is going out, then where do we get that heat? We get that heat from the gas mixture itself, right? So gas mixture, if it is 1000 for 1400 Kelvin or 1300 Kelvin, because of dissociation the temperature is going to reduce to some 1100 Kelvin or 1200 Kelvin, right? And if the temperature in the chamber reduces, what happens? The exit of the nozzle velocity reduces. If the velocity reduces, your ISP reduces, thrust reduces. So all your performance is going to get lost because of the dissociation happening in the chamber. Okay, so these are the two things. One is temperature, another is composition. Okay, two things is going to affect your ISP. So having understood that, if we want to know the ISP, we need to know the temperature, right? So now how do we calculate that temperature? So composition is already known. We already found out it's going to be 0.9 and 0.3 by 2 and zero point 0.1 by 2. So which is something like 0.15 and 0.05. Correct? Right. Composition is known. We know how many moles are present in our gas mixture. So we can find molecular weight, we can find the specific heat ratio, we can find specific heats, all these things we can find. Now the question is, how do we find temperature? Because of dissociation we have something has changed, temperature has changed. Now how do we find temperature? Any idea you guys have?
We are given the specific heats of all the three,
Okay.
so we can calculate the final temperature from 300 to the T final, or the T chamber.
See
Uh,
the okay, so but you see that from 300 to certain temperature is these mixture is not getting heated up. Ammonia is only getting heated up from 300 to that temperature. After that temperature, some dissociation has happened, and then it has reduced to lower Tc, right? How do we say that it's going to be m dot into Cp delta T? We cannot again say that, right? You understand? So the mixture of 90% zero point 0.9 moles of ammonia and 0.15 moles of hydrogen and 0.05 moles of nitrogen is not getting totally heated up from 300 Kelvin to the total temperature, higher chamber temperature. Ammonia is only getting heated up to chamber temperature. After that it got dissociated. So you can divide this as a two process. One is getting heated up to a higher temperature, and then ammonia going through a dissociation without any heat loss. So what is the physical
Okay,
concept?
so in the chamber, the NH3 goes from the 300 to the final temperature.
Mm-hmm.
Then 10% of it gets dissociated into N2H2.
Correct.
So at that point, we have to calculate, right?
Right.
So
Right.
temperature difference.
Right.
So we have the final ideal temperature.
Mm-hmm.
We are having the loss of heat,
Mm-hmm.
so we can calculate, right?
Right. So
We are
basically,
having the specific heat supply.
true. Wonderful. So it is right. So I'm trying to explain it in a easier manner. So initially you have NH3 gas, which is at 300 Kelvin. Now in the chamber, due to electrical heating, because of some power input, it has raised its temperature from 300 to 1413. How much is that? 1343 kelvins. 1343 kelvins because of some Q input, Q dot or power input with some efficiency. Because of that, we have heated up. Okay, this is from one thermodynamic state to second thermodynamic state. It has went through. Now we are telling, now there is no heat loss from the combustion chamber, but now it has reduced to 0.9 NH3. This is 1 NH3, 1 NH3, and 0.15 H2, and 0.05, sorry, 0.05 N2, and with the final temperature Tc. Okay, but here there is no heat loss. Okay, these are adiabatic systems. From this process, the adiabatic, from here to here, it's an adiabatic process. Okay, there is no heat loss from here to here. It's an adiabatic process, but during that, composition has changed, right? And also dissociation has happened. So what we should actually do is, we should apply first law of thermodynamics, or conservation of energy. So that's the basic concept you should apply. Okay, so what I'm trying to say is, the energy or enthalpy present at the state 2 of your system is equal to enthalpy present at the state 3 or final state, okay, of your system. So if you, when you equate these two enthalpies, because there is no energy loss, it's an adiabatic process, enthalpy is going to remain same, right? Delta H is equal to Q, where Q is equal to 0. So delta H is equal to remain same. From 2 to 3, once you have reached a higher temperature, you are just going through a decomposition. Because of decomposition, for for dissociation, you need some energy. So that energy is taken by whatever the energy it has within. So if it has 100 joules of energy, dissociation takes 10 joules, then at the end it will have 90 joules. If the 100 joules corresponds to 1400 Kelvin, 90 joules will correspond to some lower temperature. So in order to mathematically state, or in order to physically put this into the picture here, you are applying a first law of thermodynamics at a constant pressure. Of course, chamber pressure is constant, and then what you have is, you have enthalpy at state 2 is equal to enthalpy at state 3. So there is no loss in energy in terms of system, but within the NH3, H2 and N2, there's been energy interactions. That is what you found in the previous question. Is that clear, or did you guys confused? So
No, it's clear.
okay, thank you. So uh, then what the enthalpy I have here is not the simple not sensible enthalpy or formation enthalpy, it's a total enthalpy. Okay, because some NH3 of formation enthalpy is gone as a or some sensible enthalpy has taken into the formation enthalpy of NH3. That is what we see here. So anyway, when we solve this, you will be more clear. So enthalpy at state 2, how do we write enthalpy at state 2? It's going to be summation of any I species times total enthalpy of I. Okay, at state 2 you will have only NH3, right? So you will have n NH3, number of moles of NH3, into total enthalpy of NH3, where you can write total enthalpy of NH3 as formation enthalpy of NH3 plus Cp times Cp of NH3 times uh, the temperature of temperature T2, let's call this T2, minus 273. This is how you define enthalpy at any uh, temperature, right? If you remember back in maybe week 5 or week 4, this is how we defined an enthalpy. Similarly, at third, at stage 3, you will have summation of similarly NiHi, where we have zero point 0.9 times NH3 plus, so basically 0.15 times H2 and 0.05 times N2. Okay, so now if you want to write this, it's going to be 0.9 times delta HF of NH3 plus Cp of NH3 into T3 or T final or Tc minus 273 plus 0.15 into delta HF of H2 plus Cp of H2 into Tc minus 273 plus 0.05 delta HF of N2 Cp of N2 into Tc minus 273. The 273 here has nothing to do with T naught. It is the way we define T standard temperature is 273. So just to revisit or just to remind you, okay, and we just need to equate these two. We know NH, number of moles of NH3, you can take it for 1. So currently we are dealing with 1 only, and that is how we wrote the equation. So it's going to be 1 mole of NH3, and so we know that delta HF of H2 and N2 is going to be 0. Okay, and CpH2N2 and CpNH3 is given. So let's try this. So delta HF of NH3 plus CpNH3 into T2 minus 273 is equal to 0.9 times delta HF of NH3 plus CpNH3 into Tc minus 273 plus 0.15 into Cp of H2 Tc minus 273 plus 0.05 Cp of N2 into Tc minus 273. Okay,
I have a doubt in this.
sure.
You see, our reference is the heat of formation that we have written on the leftmost item
Right,
at
right.
next 3, which is, aren't we saying that is a standard heat of formation at 25 degrees Celsius? In that case, if that is the reference, then instead of 273, we should use 298.
True. I am sorry about that. So it's all should be 298. It should be standard. Yeah, you are absolutely right. Everything should be 298. The standard temperature is 298, so it is right. That was a mistake. So is this clear? So whatever we did here, so we might have taken a different route, or we might have taken a more laborious route, but few concepts I wanted to make sure that you understand. We could have simply wrote that dissociation energy is what been lost, and that is going to equal to mcp delta t, as Pranav said, and anyway that is also going to give you the same results. Okay, but this is a more systematic way of doing things, and uh, this will help your concepts. This will make sure your concepts are right. That's why. Okay. Do anyone have any questions in this? We are just breaking this big problem into a small concepts. Like, first is heating, and then we are dissociating. So we are just equating energies between 2 and 3, and between 2 and 3 only energy change is formation energy, and that formation energy change is supplied by the sensible energy. That is what you see here. So this formation energy change is actually supplied by the sensible energies here. Okay, that's why your temperature is going to reduce. Okay, that's the same thing which happens in a combustion, but in combustion we make sensible energy, but during dissociation sensible energy gets consumed. Okay, so that's why you have this here. Okay, I hope it's clear to everyone. Alright, let's try to substitute the numbers. So it's going to be minus 46 kilojoules, so it's going to be 10 power 3, plus Cp of NH3 is 35.08. So let me write down the Cp's. I think it's 35.06, 30 and 37. Okay, N2 is 37, H2 is 30. Joules per mole Kelvin. Cp of H2 is 30 joules per mole Kelvin, and Cp of NH3 is 35.06 joules per mole Kelvin. So if you substitute this, what would happen? 35.06. T2 we already know it's going to be 1343 minus 298 equal to 0.9 into, similarly, minus 46 into 10 power 3, plus NH3 is 35.06 into Tc minus 298 plus 0.15 into 30 Tc minus 298 plus 0.05 into 37 Tc minus 298. So can we simplify and get the answer for Tc? I hope everyone is able to follow. So let's say if I want to add all the TCs, I'm getting 37.904 into TC minus 298, then minus, I have, if I take this 46.43 on the other side, you will have 35.06 into 1343 minus 298 minus 0.1 times 46 into 10 power 3. So this side it is coming out to be 3.037.7. I'm not sure. Please check my math once. So this is coming out to be 1143 kelvins.
Yeah, I got the same.
Okay, thanks Pranav. So initially we had how much we had? We had T2 to be 1343 kelvins, and you can see because of dissociation your temperature has reduced around like 200 kelvins. It has reduced. Just 10% of ammonia dissociation has caused this problem. And now let's say if all the ammonia is dissociated, your temperature is going to be very low. It's going to be useless if it is a if we are going to use it as a thruster. Okay, so 10% ammonia is also a little high for this temperature range. To 1343 Kelvin is a very relatively speaking, it's a low temperature, so you would expect lesser dissociation. Only if when you reach 2000 or 2500 Kelvin, you will have like more dissociations. Okay, so we found the TC. We already know the composition, so then we can find the ISP, right? We already wrote a big equation for ISP. Let's use the same ISP equation. So this is the ISP equation for the vacuum conditions. Copy. Paste. So now we need to find gamma, and what else we just need to find gamma of the mixture. Now since you do not have ammonia, you are going to have ammonia, hydrogen and nitrogen as a mixture. So that you can find by finding Cp of mixture, and let's say per mole Cp of mixture is going to be summation of n, or let me write it down explicitly, n of NH3 Cp NH3 plus n of N2 Cp of N2 plus n of H2 Cp of H2 divided by n NH3 n N2 plus n H2. Okay, so this will give Cp of mixture. You can find molecular weight of the mixture. I think that is also required to find R. So you can find molecular weight of mixture, which is also going to be NNH3, molecular weight of NH3. I'm just writing for the sake of completeness. Can you guys quickly calculate and tell me molecular weight of mixture and Cp of mixture? I mean Cp of mixture, we are finding it to find gamma of mixture, nothing else.
I got CP as 34.458.
Okay, Cp of mixture is 34.458 joules per mole Kelvin. Now we need to find Cv of mixture, right? Cv of mixture is going to be Cp minus Cv is R, so Cv of mixture will be Cp minus Ru, universal gas constant. So I think it is 8.3145. How much is that? 34.458 minus 8.3145. Cv is 26.1435, I guess, joules per mole Kelvin. And if you do that, how much is gamma you are getting? Cp by Cv, 34.458 by 26.1435. Similarly, how much is the molecular weight you are getting? So once you find these two, you can substitute
58.62 something.
58.
58.62.
58.62 looks a little higher because all 17, 28 and 2, so I would expect somewhere in between.
The moles for nitrogen are 0.05, right? zero point 1 by 2.
Correct. So
And the moles for hydrogen are 0.15, zero point
correct
0.3 by 2.
correct
For NH3, it's zero point 0.9. So,
correct NH3 is
oh, wait.
17, right? Okay.
It 15.45.
15.05. Okay.
Wait, shit.
So it's between 17, 28 and 2, so I would expect somewhere in between. So similar like 15.45. This is grams per mole or kg per kilomole. Anything would work. And then gamma of mixture would be, how much is that? 34.458, 26.1435. So it is coming out to be 1.32, same as before, 1.31 and 1.32. So now,
Sir, but uh, here the R, the gas constant, I think it should correspond to NH3, right? Sorry, the mixture, right?
no, we are
The
doing it as a mole
it,
basis, right? We are doing in mole basis. If you do it in mass
uh,
basis, you should divide it by molecular weight,
okay.
right? If you do CV equal to Cp minus R, this is mass basis. These are all in joules per kg Kelvin. So what we found till now is are in joules per mole Kelvin. So if it is in mole basis, this also will get multiplied by molecular weight, right? Everything will get multiplied by molecular weight to get mole basis. So ideally you will have Ru. If it's in mole basis, you can directly use the universal gas constant. Okay. All right. So let's PE by PC. We already found what is this 5.17 into 10 power minus 4, around that. Let me go back. 5.1637 into 10 power minus 4. Now let's substitute everything here. 2 times gamma is 1.32 by 1.32 minus 1.32 into R times Tc. R is 8314.5 divided by molecular weight is 15.45 into 1 minus 5.1637 into 10 power minus 4. Gamma minus 1 is 0.32 by 1.32 whole square plus 80 times 5.1637 into 10 power minus 4 into square root of 8314.5 divided by 15.45 into Tc is oh, I didn't multiply Tc here also. How much? 1143 and multiplied by 1 by capital gamma, where capital gamma is square root of 1.32 into 2 divided by 2.32 power 2.32 by 2 into 0.32. So you find gamma here, substitute here, you will get the final ISP, and it should come less than 2200. So were anyone able to calculate? So let's say if I calculate gamma first, 2.32 and 2 divided by 0.32, into square root of 1.32. So capital gamma, I'm getting something like 0.616708. So say if I substitute that here, so this part is coming out to be 48.29, the other part is 1.67 into 10 power minus 4. This part is 2065. So 2113 Newton second per kg is what I got. It may not be right because there might be some mistake also. Please cross check once. Did anyone get ISP? So probably it should be around this only, but one thing is it's less than 2200 Newton second per kg. Okay, so this is due to dissociation. Okay, alright, it's just mathematics. You can substitute it and you can find it. Is the methodology clear? How did we arrive at the specific impulse, dissociation energy, temperature, and everything?
Yes. Yes.
So that is what I have today. Um, so if you have any questions or any questions you want to solve me, you can let me know. If you have any questions regarding the assignments, you can let me know. Do anyone have any questions? I think a few people joined after I started the question. Maybe I will quickly revise this question once more so that it will be easier for you. So what we did today was we have this resistor jet thruster where you send a electrical current through this resistance wires which is mounted on the surface of this thruster, and because of the electrical resistance this surface gets heated up, and when the ammonia gas flows through it, the ammonia gas also gets heated up, and when it gets heated up it goes through a higher temperature. So this is what happens inside this chamber. So and after that you attach a nozzle to it. This hot gases get accelerated through the nozzle, and it is going to generate thrust. Now the question was, I wanted to generate this much thrust at a specific impulse of some number, and I have ammonia gas at 300 Kelvin. Now I need to find out what is the amount of power I need to give to the electrical for this electrical circuit, so that I will be generating some hot gas, and which is eventually generates 10 newtons. And for that what we did, we first tried to find out the power required for heating is going to be the temperature change of ammonia gas from 300 to a certain temperature. That is what we wrote here. And since it the electrical heating has some efficiency here, we have efficiency factor also. And then the question was to find TC and m dot. M dot we can find it from thrust and specific impulse, which we did, and TC was the question how to find out, and we came to know that the nozzle has an expansion of 80, expansion ratio of 80, and also we have ISP, and this ISP and the expansion ratio is going to determine, and and also the pressure in the chamber is also given 0.5 megapascal. Chamber pressure, chamber temperature, and the expansion ratio is going to define my thrust, or in other words the ISP. Okay, so we use the ISP relation. Okay, if we used epsilon to find PE by PC. It turns out to be non-linear. You can either use MATLAB or you can use your scientific calculator to find out PE by PC. Once we found out, we know that ISP is a function of TC molecular weight, epsilon, PE PC, and PA by PC. Since all these are happening at vacuum conditions, these are happening in the geostationary satellite, we need to take the additionally the pressure thrust also into account. That's why we have these additional terms. So all these parameters we know except TC. ISP also we know, so we use this relation to find out the temperature. Okay, and this is for ideal expansion, but in our case it's not an ideal expansion. You have additional pressure thrust, so you should have plus additional pressure thrust you should have, so pressure term we should add. Okay, and that is what we derived here. And then we got ISP at the vacuum condition is going to have Vj plus some additional term which is going to be present, and upon expanding we get this relation, and then upon substituting everything we get the temperature. So once we get the temperature we can find the amount of the power required to heat the ammonia gas. And then what we said is, let's say we have this much ammonia gas at certain temperature, and there can be dissociation happening, right? It's a higher temperature, so we would expect dissociation to happen. So if we say 10% of this ammonia is dissociated, then what is the amount of energy loss due to dissociation, or what is the amount of energy which we when we say energy loss, it's in terms of the real performance. The performance is going to come from sensible enthalpy or the temperature, how high my temperature is, right? So in terms of that thermal energy, what is the amount of energy I lost? So for that we equated the enthalpy of formations of reactants and products. Here these are reactants and these are the products, and we found out the enthalpy of dissociation. And then we know that because of dissociation ISP is going to change, and if the ISP is changing, it is going to change because of change in temperature and also change in composition, right? ISP is going to depend on change in temperature and composition. In addition, it will also depend on expansion ratio, P by PC, all those things, but those things are not going to change. Those are system parameters. So only these things are going to change. So we already know the composition from the previous question, and or we already said that it's only 10% as dissociated. We wanted to find the temperature. So to find the temperature, we applied first law of thermodynamics from state 2 to state 3, okay, and then which is nothing but delta H is equal to 0 or H2 is equal to H3, and we just equated the total enthalpy of before dissociation and after dissociation, and then we came to know that temperature has reduced. So the temperature reduction happening because some amount of sensible enthalpy has been lost due to dissociation, and the amount of lost is what we found in the previous question. In this question we found out what is the temperature lost, or what is the temperature change. And once we found the temperature change, we have all the parameters to find the ISP. We substitute in the equation, and at the end we found the ISP, and as expected the ISP has reduced because of dissociation. So we have like 100 Newton second per kg, which is around like 10 seconds has reduced because of dissociation in terms of seconds. All right, so I hope it's clear. I think similar question, you may not be able to, you may not be asked to find change in ISP, but I think you were asked to find amount of energy lost due to dissociation and all the other things in the in your assignments, I guess, week 12 assignments. So we will do one or two problems next week about the nuclear rockets, which would also help you solve the week 12 assignments, and then we might have one more session to revise for the revision of whole whatever, like whole course, whatever we have studied in this course. Okay, any questions you guys have?
So that one, that revision one will be on next Saturday, or means the last
So
Saturday, or
actually, what we will do is we can have a two revision sections, okay. So because it's already been told that we will have one on 18th. I still didn't get confirmation. We will have one on 18th of April, which is Thursday, and we can also have it on 20th of April, which is Saturday. But most likely officially it will be 18th on Thursday, but I am fine with taking one class on Saturday. It's not a problem. Okay, I can repeat the same thing during revisions if you guys are not available. Okay, or if you guys are available, you can come and ask questions, no problem. But I still didn't get confirmation yet from NPTEL, so let's see. Probably we can confirm it by next week's class. Okay.
sure, sir.
Okay. All right. Any questions? If there are no questions, we'll meet next week. If you have any questions, you can stay back and ask. I will be here for another few minutes.
On my side, thank you so much. It's all clear.
Thank you, sir. Thank you for attending.
Sir, like in the second question,
Mm-hmm.
they were saying that only the 10% gets dissociated, or like only gets 90% of the NH3 is useful.
Right, right.
So, so why does it happen? Means, what happens in the chamber? Is it due to uneven temperature distribution?
No, so basically, it is not due to any of that. The dissociation in principle happens because of high temperatures. If you have high temperatures, what happens is the your temperature is nothing but if from a molecular theory, a kinetic theory of gases, temperature is nothing but the velocity of molecules, what the fluctuating velocities of molecules will say, right? The each and every molecule will move at different velocity. It's a random velocity, and if the temperature is high, these molecules will, the speed of the molecule speed of the molecules are higher if the temperature is high. If the temperature is low, the same speed is lower. So if you have a higher temperature, there is a possibility that two ammonia molecules which is moving at a very high speed can easily collide, and when they collide they can reach a higher activation energy, which is equivalent to that activation energy is enough to dissociate this ammonia molecule into N2 and H2. So that is purely coming from the molecular theory. So because of the random motion and high speed motion, the collisions can happen, and some collisions in that will have enough energy for it to dissociate. That is the main reason this dissociations happen in the chamber.
Okay. So, are there any measures or steps taken to avoid this thing, or minimize this thing?
So there is no way you can avoid this. This is something bound to happen because you cannot stop the fast moving molecules of ammonia. You know, if you, only way is you need to reduce the temperature, but if you reduce the temperature, you will lose the you know, performance. uh, I
We
mean,
will lose performance.
right. So but you can reduce it to a certain amount and still gain the performance, because of dissociation there might be some performance loss, right? So upon reducing the temperature of the chamber, so that's why people use a little lean mixture or to reduce the exit temperature or reduce the chamber temperature. That is the only way. Changing the temperature is the only way, or you can dilute the, you know, combustion products, but that will also affect the uh, overall mixture specific heats, which will again affect the uh, overall molecular weight, and which will affect the performance. So this is something we cannot avoid. This is something it's bound to happen, and yeah. So there is no other way we can reduce it. It's not coming from the system. It's not coming from the uh, external parameters. It is within the, it is internal inefficiency. We cannot do anything.
So, just a curious question:
Mm-hmm.
if we are using like ammonia
Mm-hmm.
in certain small rocket motor,
Mm-hmm.
and now since we have hydrogen here, we have H2 molecules,
Mm-hmm.
we we have a high temperature. So can we dilute its very small amount of oxygen so
Mm-hmm.
that it can combine and it can also add up to the ISP?
Right. So you were you wanted to add some oxygen and then make combustion happen there, right?
Yes, a
You can.
small amount which
Yeah.
would be corresponding to the hydrogen mass.
So if you add that, there are few things. So you, let's say the amount of oxygen you add. Let's say you take the, how much did we got here? Let's say you take 0.15 moles of hydrogen is there. Let's say you had another 0.15 moles of oxygen you introduce, and you can have a combustion there, and you can get a, H2O as a product. Okay, that is possible. uh, but how much that is going to improve, we need to do an analysis and see whether that is helpful or not. True, you can do that.
I think we need to keep it on fuel rich side, because if we go on increasing a bit more oxygen, then the excess oxygen would absorb some energy that would also decrease the ISP.
Yeah, CP of
But keeping the but starving the hydrogen of the oxygen, we can certainly remove the hydrogen also. So
but
there's no loss.
that is true. That is true. What you will also have is because of hydrogen and oxygen, the temperature can reach. So now you have reached only 1400 Kelvin. You could reach 2500 Kelvin. So that is a huge jump in, huge increase in temperature compared to, uh, increase in CP, which is going to affect your performance. So yeah, I mean, whether you will have that much increase in temperature is also a question, right? So there are different parameters, as you said. There's going to be amount of heat released, which is going to increase the sensible energy part, and there's going to be amount of CP rise or CP decrease, which is going to uh, affect the temperature again, and there's going to be the molecular weight of the mixture, which will be difficult to accelerate in the nozzle. So if there is an increase in molecular weight, that will be little difficult to accelerate. So all these three important parameters going to affect. So based on this, you can change the equivalence ratio, maybe in the rich side or lean side, and you can find a optimal point which is going to improve your performance. You are right.
Okay, sir. Thank you, sir.